Hi, welcome. We all know that meteorites can be catastrophic. Just look at the Chicxulub asteroid that wiped out the dinosaurs, or the 1908 Tunguska event, which hit Siberia with the force of a nuclear explosion. But what if a massive meteorite strike billions of years ago actually helped life flourish on Earth, rather than destroying it? A recent study reveals that a colossal asteroid, much larger than the Chicxulub asteroid, collided with Earth billions of years ago. Surprisingly, this catastrophic event didn't lead to doom. Instead, it paved the way for life to emerge. But how is that possible? How could one meteorite shape the course of evolution? And what would our planet look like today if this event never occurred? Let's break it down. Billions of years ago, when Earth was in its early stages and life was just beginning to form, the planet was anything but calm. Several massive asteroids struck, causing immense damage and reshaping Earth's surface. Evidence of these impacts remains visible today in ancient rock layers on Earth and craters on the Moon's surface. Scientists studying the Archean Eon have identified at least 16 major asteroid impacts, each one over 10 kilometers wide, about the same size or even larger than the asteroid that ended the dinosaurs' reign 65 million years ago. While we have a good understanding of the impact of the dinosaur killer asteroid and its effects on life on Earth, the earlier collisions are still somewhat unclear. How did these massive impacts influence Earth's environment? And what was their impact on the primitive bacterial life forms already starting to form? These questions are crucial because for the first 2 billion years, these giant impacts occurred roughly every 15 million years, between 3.5 and 3.2 billion years ago. We have clear evidence of these enormous impacts, and we're not talking about small events here. These were asteroid strikes of a scale comparable to the ones that wiped out the dinosaurs, likely causing mass extinction-level events. Yet, life somehow survived. Early life forms endured, adapted, and even flourished after these catastrophic events. So, why didn't life go extinct? What happened to those early life forms during these massive impacts? To explore this, scientists have focused on one particularly colossal impact, the S2 meteorite event, which occurred around 3.2 billion years ago. This asteroid was estimated to be at least 200 times more massive than the one that ended the dinosaurs. Despite the devastation it caused, this impact may have played an unexpected role. It might have helped jumpstart life on Earth in ways we're only beginning to understand. Keep watching as we delve into this terrifying yet equally fascinating meteor event and its influence on the evolution of life on Earth. To begin, let's set some important context. Meteorites are older than our planet, dating back about 4.5 billion years. These space rocks are ancient fragments of asteroids, planets, and even comets, traveling through space before landing on Earth's surface. Here's how it works. A meteorite strike occurs when a space rock, known as a meteoroid, crashes into the surface of a planet, moon, or another celestial body. This marks the dramatic end of its journey. It all begins when a meteoroid, a small fragment of a comet or asteroid, enters a planet's atmosphere. As it speeds through, intense friction and pressure cause it to heat up and glow brightly, creating what we call a shooting star. If the rock is tough enough to survive the heat and reach the ground, it's officially a meteorite. Meteorite strikes can vary greatly in size, from tiny rocks that barely make a dent to massive collisions that leave huge craters behind. For instance, some meteorites are so small that we call them micrometeorites, which fall to Earth daily without us even noticing. Around 40,000 metric tons of micrometeorites land on Earth each year. On the other hand, larger meteorites, known as bolides, can light up the sky with explosive displays. It's the bigger meteorite strikes that often make headlines. We typically associate massive impacts with catastrophic events, like the Chicxulub asteroid, which struck Earth 66 million years ago. This was no ordinary space rock. It measured between 10 and 15 kilometers in diameter and struck with the force of 1 billion atomic bombs, traveling at a speed of 20 kilometers per second. The asteroid hit what is now the Yucatan Peninsula in Mexico, creating a crater more than 150 kilometers wide. The impact sent massive plumes of sulfur and fine dust into the atmosphere, blocking out the sun and triggering an impact winter. The temperature plummeted, causing plants to die off and ecosystems to collapse worldwide. This environmental disaster led to the extinction of about 75% of life on Earth, including the dinosaurs, which had dominated for over 200 million years. While meteorite impacts are often associated with destruction, recent studies suggest that they may do more than just wipe out ecosystems. Could an early meteorite have actually helped kickstart life? To explore this, we need to examine the S2 meteorite, a giant space rock that struck Earth during the early stages of the solar system. Far larger than the Chicxulub asteroid, the S2 meteorite may have had unexpected positive effects on Earth. Although its size and impact would have caused significant disruption, a recent study suggests it could have acted as a gigantic fertilizer bomb, contributing to the conditions necessary for life to form. A study led by Harvard University geologist Drabin suggests that the S2 meteorite, which struck Earth over 3 billion years ago during the Paleoarchean era, played a crucial role in the planet's early life. This massive space rock, estimated to be 50 to 200 times larger than the Chicxulub asteroid, unleashed a cataclysmic event upon impact. The strike was so powerful it could have instantly vaporized the meteorite, sending a massive cloud of rock vapor and dust into the atmosphere, darkening the skies. Additionally, the intense heat from the impact could have boiled the upper layers of the oceans. While such an impact would have been devastating, Dr. Drabin's study suggests that the S2 meteorite's effects may not have been entirely destructive. The immense heat. The chemicals released during the S2 meteorite impact could have created conditions that, paradoxically, helped life form and thrive. Dr. Drabin suggests that the vaporized materials from the impact may have provided a rich source of nutrients, potentially supplying the building blocks necessary for life to flourish in Earth's early oceans. This event may have triggered a chain of reactions that eventually led to the emergence of the first complex life forms. During the Paleoarchean era, Earth was frequently bombarded by large meteorites, with impacts occurring roughly every 15 million years. While these events were typically catastrophic, Dr. Drabin argues that the S2 meteorite was different. While he acknowledges the immense destruction caused by the meteorite's impact, his research shows that life quickly recovered as Earth's conditions improved. In fact, life didn't just bounce back, it thrived. This rapid recovery is linked to the idea of a fertilizer bomb, where the impact enriched the environment, making it more fertile and helping life flourish again. Andrew Null, a co-author of the study, further explains that the S2 meteorite was a type known as carbonaceous chondrite, which contains high concentrations of carbon, phosphorus, and other essential elements for life. When the meteorite struck Earth, it released these vital elements into the atmosphere and oceans, enriching the environment. This influx of nutrients likely acted as a catalyst, promoting the development of early life. As Earth's conditions stabilized after the massive collision, the planet underwent extreme changes. The skies darkened, and weathering and erosion on land intensified. We can still see evidence of these changes in some of the ancient deposits. While such conditions would have wiped out modern life, ancient life somehow persisted, and what's even more fascinating is how this event impacted photosynthetic life, those organisms that use sunlight to create energy. One of the first outcomes after the impact was a massive tsunami, which stirred up minerals and metals from the ocean floor, redistributing them across the planet. This played a pivotal role for life in the ocean. Before the impact, photosynthetic bacteria that relied on dissolved iron to convert carbon dioxide into sugars weren't thriving. These microbes lived in the upper ocean layers where sunlight was abundant, but iron, a key resource, was scarce. After the impact, however, the tsunami brought enormous amounts of iron from deeper ocean layers and the Earth's crust to the surface, creating an environment where these bacteria could thrive. Initially, the devastation caused by the impact likely wiped out much of the photosynthetic life in the upper ocean layers. But within just a few years, as conditions stabilized, something remarkable happened. A massive bloom of new photosynthetic life spread rapidly across the planet. This new burst of microbial life, thriving in the iron-rich waters, led to a boom in biomass. What began as catastrophic conditions, dark skies, raging tsunamis, and widespread destruction, soon transformed into a thriving biosphere. Microbes that relied on iron for photosynthesis flourished, marking a turning point that spread life far and wide across Earth's oceans. This remarkable recovery set the stage for something entirely new, the evolution of more complex life forms. Thank you for watching. If you enjoyed the video, please press the like button, and if you're new, please subscribe and turn the notification button on so you don't miss our future videos.